I was just looking to understand what the process of convection is, what the structures look like, how things behave and evolve. I didn't know what was going on, and so when I looked at the visualizations, it helped me understand what was going on. And then I would talk to people who actually observe the sun, and I'd find out what they were actually seeing. My name is Robert Stein, and I'm a professor emeritus at Michigan State University in the Department of Physics and Astronomy. I guess from the very beginning, I was interested in fluid dynamics, which is how fluids behave. When we say fluids, we don't just mean water or things like that, we also mean gases. I was interested in the atmospheres of stars. I first started off doing some stuff in the evolution of stars, but again, that's sort of fluids because stars are gases and we were interested in how they behaved. Everything I've done in my research career has used computers. I think I have worked on almost every supercomputer that has existed. I started with an IBM that had vacuum tubes and a rotating drum memory with 2,000 words of storage, not bytes, words of storage. We wrote the codes in and put it through some kind of pre-compiler, and it punched you out a new set of cards in symbolic assembly language, which you then put on the right place on the drum so that in the time it took to execute an instruction, the drum would have rotated around once to just reach the next instruction. As the power of computers increased, two things happened. We went to do more complex problems, including more physics, and we could do them on much larger scales. If you're studying something here on Earth, you can handle it and you can run experiments to see how it behaves. In astronomy, we can't take a chunk of the sun, and so we have to observe it from a distance. All of the information we get in astronomy comes from the light that we analyze. So astronomers have become experts on getting the last little bit of information out of light. Astronomers use telescopes mainly as a big light bucket. Our eyes, only a certain amount of light can go in them. You make something that's huge, and a lot of light goes in, and the bigger it is, the more light it can collect. We use as big telescopes as we can to get as much light as we can. When you have a lot of light, you can break the light down into very narrow color bands, and so you can get a lot more information out of it. There's a side effect also for the sun, which is what I'm interested in. Because the sun is close enough, we actually see its size. If you take a picture of it with a telescope and you can enlarge it, you can look at a little piece of the sun, you can see fine structures on it. We can see things on the sun that are about 70 kilometers in size right now. And we're building a new telescope that should be able to see things that are about 30 kilometers in size. And for the sun, that's really very small scale. And of course, the more information we get means there's more stuff to model because there's new things that we see that we never expected to see. So you've got to go back and want to model things on finer structures and shorter time scales. And so you need bigger computers that are faster that can model this thing better. If you were to just make a model without anything to compare it with, you wouldn't know if it was right or wrong or nonsense. It's only by comparing the results of these simulations or models that we make with what's actually seen that we have some confidence that we're doing something right. When we say we simulate something, is we're making a model of it. but it's a model that involves solving a set of equations to figure out how this thing behaves. And those equations are solved numerically on a computer. So it's like making a model of something. You make a model of a car, or a plane, or in my case, what happens in the convection on the sun. When we get into these large-scale computations, you can't look at numbers. You can't make any sense of it. You have to picture it some way. There's lots of programs that help you do that kind of analysis. You can make one-dimensional graphs, you can make two-dimensional images. And sometimes in order to really see what's going on, you actually need a 3D picture. In this animation, our goal was to see how magnetic field comes up through the surface of the sun and what effect it has. We start by looking down on the surface of the sun, and we see a pattern of bright and dark regions. The bright regions are where it's hot, and the dark lanes around them are where that gas has cooled off and starts being pulled back down by gravity and goes back down into the interior of the sun. And then perspective dives below the surface of the sun. We're looking at the magnetic structures. What we see are visualizations of the current, and we also see field lines tracing the structure of the magnetic field. And we see that it starts off as a sort of large loop, which then breaks up into sort of little finer structures as it's rising up towards the surface. It's actually being brought to the surface by two effects. One is that it's buoyant, so it's floating up to the surface. And the other is that it's in one of these rising hot fluid columns, which is carrying it up to the surface. The convection itself is bringing it up to the surface, but it's also breaking it down into much finer structures. So as it gets near the surface, and the convection itself develops these much finer structures. You see it then coming up, and it has all of this fine filigree kind of pattern as it comes through the surface. Because it was part of this large loop of magnetic field, it has these legs which are going way down deep into the sun, and they stay there. That's what forms the active regions where you get the sunspots. It has become dark because the magnetic field in these legs has inhibited the convection from carrying heat to the surface, so it has cooled off. And when it cools off, it becomes darker. Every time I talk to people who are observing things and they give me new ideas about what I should look for, I go back and I look at things in a new way and I discover new things. Science actually makes people interested in the world around them and makes them look at what's around them and think about why things are the way they are and what makes things work the way they work. People can begin to see that it's exciting, so that young people will want to have careers in it, because if you don't have young people entering the field, it's going to die out. And also that people understand that it really makes a difference.